Hello and welcome to this video about the periodic table. In this video we're going to look at Mendeleevs' organization of the elements, how he did that, how the periodic table is organized, electrons and different elements, and the electron dot diagram. So where did the periodic table of elements come from? In the late 1800s, a Russian chemist by the name of Dmitry Mendeleev he presented a way to organize all of the elements that were known at that time. He studied the physical and the chemical properties of the elements, and he found that these chemical properties repeated themselves in very predictable patterns. And because of that, it was considered to be periodic because they were repeating. Here is an example of one of Mendeleev's early periodic charts. He arranged the elements in rows based on increasing atomic mass, and then he arranged them in columns based on elements that shared similar properties. And today, the arrangement is called the periodic table of the elements, and the elements are arranged by increasing atomic number. Remember that increasing atomic number is the number of protons instead of increasing atomic mass like Mendeleev did. And also in the same way, we arrange them by these periodic changes in the physical and chemical properties. Here is a periodic table from around 1915, a little closer to what we recognize as it looking like today. And it's important to note, too, Mendeleev actually, he had holes in his periodic table where those elements were not known or discovered yet, but he predicted the properties of those elements to a surprisingly accurate degree. And when those elements were later discovered, they were found to correspond to Mendeleev's predictions. That's because of the trends that we see on the periodic table and just the amazing periodicity of those trends. So let's take a look at this modern periodic table of elements, and let's look at a few terms that we should know. First of all, the rows that are going across, we call these periods, and they are numbered 1 through 7. The columns that go down are called groups. Sometimes they're called families as well. And elements in the same family share very similar properties. For example, this family right here, these elements all share very similar properties. So we will look at some of those specific families as we progress through this unit. But one thing to note on the periodic table, you can see how we start with the atomic number 1 for hydrogen. And then the next element that appears is atomic number 2, over here, helium. Then atomic number 3, 4, 5, 6, 7, 8, 9, 10. Those are the number of protons, remember? And go up to atomic number 11, 12, 13, 14, 15, 16, 17, 18. And you can see that each one of these elements has a different atomic number. They have a different number of protons that gives it its identity. And they are arranged by increasing atomic number as we go across on the periodic table. Another thing to note is that right here, if you were to cut this periodic table and you were able to insert, we could cut a little line right here and insert these two rows right here in the periodic table and basically make a very, very wide periodic table. That's really how it should look. These are always listed down below because by including them at this point in the periodic table, it makes the periodic table too wide to be usefully read and makes the numbers too small and it doesn't fit on a nice sheet of paper. So those are always put down here, but they really belong right there in the periodic table. We can also divide the periodic table of elements into groups of metals and nonmetals, and there are also a few metalloids. So these elements here that are in green, those are all of the metals, and you probably recognize some of them: gold, nickel, copper, iron. Those are metals. Some of these you might not realize. Sodium is a metal. Potassium, calcium, those are metals as well. And metals, general properties of metals, they conduct electricity well and are generally shiny or lustrous. They can be drawn into a wire, or they're also malleable and can be hammered into different shapes. These red elements here that are colored in, those are nonmetals, and they do not have properties of metals. They do not conduct electricity well. These elements right here are metalloids. They have some characteristics of both. It's good to familiarize yourself with the things that are nonmetals, the things that are metals, and which ones are metalloids. The metalloids follow this little stair step on the periodic table, so you can always remind yourself where the metalloids are that way. So we've talked about the periodic table being arranged by increasing atomic mass or numbers of protons. Now what about the electrons? Let's talk about electrons for a moment. Remember the negatively charged particles that are somewhere in that electron cloud around the nucleus. How many electrons would be in these different elements? Well, because a neutral atom does not have an overall charge, the number of electrons is going to be equal to the number of protons in a neutral atom. So how many electrons would, say, carbon have? Well, we know that carbon's atomic number is 6, has 6 protons. Since it's a neutral atom, it's going to also have 6 electrons. I'm going to have a plus 6 charge and a negative 6 charge from all those electrons. That will give me a total of 6 minus 6 equals 0. Likewise, how many electrons does aluminum have? Well, it has 13 protons. So then it also has 13 electrons. So electrons are located in that electron cloud that surrounds the nucleus, and they also have different amounts of energy within that electron cloud. We can draw a model for that by placing electrons in different energy levels. Here I just placed 2 electrons in this very low energy level. Electrons close to the nucleus have lower energy than electrons further away. Electrons also occupy energy in very, very specific patterns. Elements that are in the same group or family going down the periodic table have the same number of electrons in their outermost energy level. We call those electrons that are in the outermost energy level, here this would be the outermost energy level, we call those the valence electrons. And all of these elements right here would share the same number of valence electrons. These elements here share the same number of valence electrons because they're in the same family. Now these energy levels, interestingly enough, coincide with the rows on the periodic table. So the energy levels are named using numbers 1 to 7, and there are maximum numbers of electrons that different energy levels can hold. If we look at this, energy level 1, we only have hydrogen and helium that have valence electrons in energy level 1, and the maximum number of electrons that energy level 1 can hold is 1, 2. Here we have energy level number 2, and the maximum electrons that energy level 2 can hold is 1, 2, 3, 4, 5, 6, 7, 8. Only 8 electrons will fit in energy level number 2. It's kind of shown here on this diagram. We have energy level number 3. Energy level number 3 can actually obtain more. It can hold a total of 1, 2, 3, 4, 5, 6, 7, 8, but it can also hold 10 more right here. So 18 is the maximum number that energy level 3 can hold. And the pattern continues based on different energy levels. Now, elements are very stable when they contain the maximum level number of electrons in their outermost energy level. For example, 2 electrons can fit in that first energy level. Helium is incredibly stable because it has 2 valence electrons. Look at neon. Neon has a total of 10 electrons. 2 in the first energy level, and 1, 2, 3, 4, 5, 6, 7, 8 in the second energy level. It has a full second energy level with 8 electrons in it. Call that an octet. It's a very, very stable and a very happy element because it has a full outer energy shell. All of these are called the noble gases because they all have full outer energy shells full of electrons. So one way we can represent valence electrons is through an electron dot diagram. In an electron dot diagram, we write the chemical symbol for the element, and then we have dots that represent the valence electrons for that element. We have helium right here. It holds 2 electrons. 1, 2. You can see helium on the periodic table there. And so we represent those 2 valence electrons in this electron dot diagram like that. Here are the other noble gases with their electron dot diagrams represented. Here's the electron dot diagram for sodium. It has simply 1 electron. You can see it right here on the periodic table. It only has 1 valence electron, 1 electron in that 3rd energy level. And all of these elements, in fact, have the same electron dot diagrams with just a different chemical symbol. Lithium also has 1 valence electron, potassium, rubidium, cesium, and francium. Chlorine, on the other hand, is clear over here on the periodic table, right there. It's halogen, and it has 7 valence electrons. You know that because you have 1, 2, 3, 4, 5, 6, 7 electrons that are in that 3rd energy level. And so chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. In fact, all of the halogens, everything in this family, has 7 valence electrons. What's interesting is that when sodium and chlorine are near each other, chlorine would really like to have 1 more electron because then it could have a full octet, a full outer energy shell with 8 electrons in it. Sodium would really like to lose an electron because then it could have a full octet and it could have 8 electrons in its 2nd energy level rather than having this dangling extra electron in the 3rd energy level. So when these two combine in a bond, chlorine will take 1 of those electrons away from the sodium. When sodium has 1 less electron, it becomes a positive 1 charge. And then chlorine, when it gains that electron, becomes a chloride ion with an extra negative charge. Advanced ideas? Look at neon signs. How do they actually work? What's going on with the electrons? What are quantum numbers? What do they describe? What are some different shapes of the different electron orbitals? What's different about them? What's the Pauli exclusion principle? Or maybe you have some other ideas. I look forward to seeing what you come up with, and we'll see you in class.